videos number 17 and 18, I showed how to build and program a 16-channel servo decoder, and while servos in my opinion are the most elegant way to control turnouts and signals, I am aware that many folks use either single or dual coil switch machines or slow motion stall motors. So it is time to add support for those switch machine types as well. Hello YouTubers and welcome to the Internet of Toy Trains. I am Hans Tanner and here is a new episode of IoTT with fresh ideas about how to use the Internet of Things along with sensors and microcontrollers to control a model railroad layout. So, get on board! The train is leaving the station. Here is the table of contents of this video so that you can skip ahead to the topics you are most interested in. To understand the requirements, let's have a look at what we are going to control. Typical devices are motorized switch machines and such with magnets. Motorized devices have a DC motor with polarity selected based on the desired position. It then runs to the end of the mechanical course and either stalls or is switched off by limiter switches. In either case, we can use two relays to supply the required polarity and then leave it with that. The same is valid for two-wire solenoid switch machines. Only in this case, we need to switch off the power after a specified amount of time or the coils will overheat and get destroyed. Three-wire solenoid switches are different as they also need a pulse for activation, but it needs to be delivered to different wires. One wire is for thrown, one wire for closed, and the third wire is common, which can be plus or minus, or in the case of some systems, just one of two AC wires. Because there are a wide variety of current types for driving different switch machine brands, I think it is best to use relays to control them. This way, it is easy to supply whatever is needed. An electronic alternative would be using H-bridge drivers, but they could only supply DC unless we would like to make things way more complicated. So, the idea is to use two relays for each turnout and control them using two I/O ports of the Nano. For this I am using a 16 relay board from SainSmart, and since the Nano only has 12 digital I/Os, we are going to use a 16-channel port expander. You find links to all those components in the description of this video. The port expander can be controlled using the I2C bus, and we could connect a maximum of 8 expanders, so 64 turnouts would be feasible. The first device to place is this 16-channel I/O port expander. It has an I2C bus connection on this side, so we can talk from the Arduino to that device, and what it does, it provides 16 1-bit I/O ports that can be used to control relays. They could also be used as inputs, but we are going to use them as an output. So I'm placing it right next to the PWM driver, and what it needs is VCC and ground, and SEL and SDA for the I2C bus, and then the other three connections are the reset pin and two interrupts we are not going to use. So what we need to do is putting on VCC and ground. Now VCC, this time I'm going to take from the 5-volt pin of the Arduino, which is right here. I could supply it with 3.3 or 5 volts, both would actually work, but it needs to be the same voltage as we are going to use on the relay board. The relay board would actually also work with 3.3 and 5. The important thing is we need to select the same voltage for the relay board and the I/O port expander, otherwise there will be some difficulties with controlling the I/Os. And the reason I'm picking 5 volts is that the voltage regulator on the Arduino provides more output current on the 5 volt port than what is available on the 3.3 volt port. And since on the relay board we are using optocouplers that have a little bit higher power consumption than just a simple IC, I'm going to select the 5 volt. The second thing we need to connect is the ground, and we can simply bridge from the PWM driver to the ground connection of the port expander. That's it. And then we need SCL and SDA, just as we had it before. So they are basically just connected in parallel. So the gray is gonna be SDA and the white is SCL. That's it. So now for the relay board, and I have already prepared that. It requires 5 volt and ground, so VCC and ground. And for the relays, so that's for the logic. And for the relay, for driving the relay coils, it requires 12 volts. So 12 volts, I'm lucky here because the whole thing here is connected to N-scale voltage. So what I'm getting at the output of my DCC interface is about 13 volts. That's close enough to 12. So I'm basically just connecting the voltage to the input of the buck converter. So the ground goes to the negative side here, and the 12 volt goes to the positive side here. That will do the trick. And then I need 5 volt and ground, which I can connect to the 5 volts here on the Arduino. Now I just need to make sure actually the white one is 5 volt right here, and the ground actually goes right next to it here, to the ground connector. That's the black. Okay, black is ground, goes to the ground connector on the relay board. Okay, that's it. Now the only thing I need to connect are my 16 IO port lines. So here it's actually labeled PA, port A from 0, 1, 2, 3 to 7, and then PB, port B from 0 to 7 in the other direction here. And they represent IOs 0 to 15. So I get started here with PA 0. Then 1. I'm going to shorten that in the video and show you just the result of it, since connecting that really is a little bit boring to watch. Okay, the hardware is connected, so now let's put power on. I connect DCC to my 2 jumper wires here, and here we go, and we can test our servos. Yes, they still work. So everything is good. Time to start developing the software. As seen before, the first step in developing the software is making sure that that hardware actually works and we can control it properly. So what we do is first we install a driver for that MCP 23017 board. So we go to Tools, Manage Library, and Adafruit again has a nice library for that port expander. So we key in Adafruit MCP and we get it, Adafruit MCP 23017. It shows it's installed already. If you don't have it, click on the install button and you're good. And no surprise, as seen last time, as soon as you install a library, it's likely to install some examples. So we go to examples, Adafruit, and we see here MCP 23017, and we take the toggle example. So we load it, make it full screen, and we see it loads the definition. It defines a variable for that driver, and then it has a setup and a loop structure. In the setup it initializes that variable, and then it initializes one output pin. And in the loop section, actually it's just toggling that pin. It goes from 0, for port 0 it goes from high to low and does a little break and then just cycles around, so that relay would flip every 100 milliseconds. Of course, for testing the board that's not good enough. We want to have a solution that cycles through all 16 relays. So let's make a few changes here. First, I want to be able to print out something, so I initialize my serial port, and then I do a for loop to initialize the pins. So I do a structure that cycles through all 16 pins. And what I do in that structure, first I initialize the pin. Of course now it's pin I make it an output, and then in the next step I set an initial value high. I could also put in true or put in 1, that would be the same. So we set the output value to high, which switches the relay off. It's kind of like inverse logic. If I write a 0, the relay goes on. If I write a 1, the relay goes off. So that's it for the initialization. And then for the loop, I just copy that. Actually, I copied the whole thing and delete a few things later on. We make it as simple as possible. So I cycle through. The next command here I don't need because it's already initialized. Then I set the value, and I set the value to the inverse of what it is. So I do a digital read of port I, and I basically just say do the other thing. So a not, I set port I to not port I, so that makes it flip. And I would also like to print out that I'm doing that. Including the port number. And whether I'm setting it to on or off. And the thing is, for that I read the port, I read the status of the port, and then say if it is set, I print to off, and if it's not set, I print to on. So I basically read the input, make a decision based on that. If the input is set, so true 1, I say I'm setting the port to off, and if it's 0, I'm setting the port to on. And then I do a little delay, so just that we can actually watch it and it's not just rattling through. So I do like a 200 millisecond delay. And then once I cycled through the whole thing, I do like a 2-second delay, and that's it. Let's compile and try, see what happens. And I can put up the serial monitor and we would see what it's doing. It's done with compilation, was successful. Now it's uploading, it's done, and it's now cycling through. Okay. Okay, that seems to work. All the LEDs are coming on, so success. Okay, for developing the software I'm going in two different steps. The first step is more like a cleanup and preparation step, and then in the second step we are going to implement the support for the relay board. To prepare, I have a few things I would like to clean up on the current software. The first thing is I would like to have individual rotation speed for the servos when going up and going down. I saw that in a video about another product and I thought that's really a nice feature. So let's put it in as well so that we can actually configure the servo going fast in one direction and going slow in the other direction, and of course with individual speed settings. The second thing I would like to do, as you remember, all the servos are now controlled from an array, and the port the servo is using is really given by the position in that array, and I would like to make a change to that so that I can give an individual port to each servo, so independent from where it is in the array, even if it's like at the start it could have like port number 15 on the PWM driver, so I'm going to change that. The reason for doing that is that I can actually switch around between relays and servos later on, so it really does not matter what type an output is. It can be anywhere in that list and just be addressed. The third thing I'm doing in preparation for adding the relay board is I'm going to specify a device type for relays so that I can distinguish in the configuration, is it a relay or is it going to be a servo. And I'm also going to prepare the structure for processing relays and servos differently. So we will see that. Let's go back to the IDE and start making those changes. First thing is kind of like a cleanup thing. Now that we are going to deal with relays as well, I'm simply making this DCC address and no longer a servo address. Then I'm going to introduce an 8-bit unsigned integer. I call it, no, not servo, I call it drive type. And drive type could be either a servo, what we already have, or it could be relay, and so that goes in the configuration. And then, as talked about, I'm going to define a 16-bit unsigned for the port, and actually I'm going to define 2 ports because a servo is only using 1 port, but as we have seen, for controlling a switch machine we need 2 relays, so we need to have 2 ports. So I'm doing a port A and I'm doing a port B. And in the case of a servo where only 1 port is used, really we just leave one. We only use one. We only use port A for the servos. We still give a number to port B. We make it the same as port A, and it's just simply not used. And then to deal with the different speeds in the rotation, we make this a move delay CL for closed, and we copy it and also make a move delay TH. And then the last thing I would like to do here, we called this last move, and I want to change that thinking process around and want to make this a next move. The reason is last move, as you remember, I was setting that last move variable at the time when I did an activity in moving the servo, and then I compared that last move time, added to the last move time my delay time, and compared that to the current time, and if current time was actually greater than this addition, I took the next action. Now that means every time I'm going through there I have to make that addition. So I'm changing that around. I make that addition just once at the time when I calculate the next time, and then I have to compare the current time only to like one variable without additional computation. So that makes the code executing faster, and we are looking for speed, of course, all the time. So that's it. Now let's look into what that means. We now have the DCC address, then we have our drive type, which is servo, then we have port A, port B. Let's get started with that, and we do it just like that. 1, 1, 2, 2. Okay, so that's the first part, and then back here we need to give it a second delay time. Like in the first one, we already have 10 milliseconds for delay in the close direction, and we give it like a 0 in the other direction. So in general, I'm just putting in an additional 0. I'm just making 2 examples here for the third line here, where that's my second servo. As you remember, I only have implemented every other. I do it the other way around, so I give it a 10 as the second timer variable. So that means the first servo should go up slow and fast down, and the second servo should go up fast and slow down. So we will see that. That's basically just for testing, and everything else, oops, is getting a 0. So I just copy that. Okay, here. So that should be the configuration. Now let's quickly look through the code, what we need to change. Here we need to make this DCC adder. Same goes here, we need to make this DCC address. Everything else I think remains the same. And then process locations. Here I'm going to set up a structure that we can actually process servos and relays. So it's not a process location becomes sort of the umbrella function that calls 2 different functions, one being process servo, which is pretty much what we have here, and the other one process relay. So let's get started by defining this process relay. Oops, wrong. Okay, and then we need this. We make process servo, and then actually we can copy. Well, let's now start a new function here, process locations, which is the one that is going to be called from our loop function down here, process locations. So it calls this one here, and from here we see what it actually is, and then call either process servo or process relay. Now, since we call that individually, we just can copy that loop part here into our new process locations. It goes right here, so we go through it, see if target position is the same or is different than current position. If so, we see now, we check now what drive type it is. So we do a switch statement, and what we look at is the drive type. And depending on the drive type, we say if it is a servo, we do process servo, and of course now we process that only for that particular servo line, for that particular line in the array. Oh, come on. Okay, and then we do a break here so that it skips the rest, and then we do the same thing for relays. So this becomes relay, and we would process relay with the same with that particular line, and then we need to close everything up. So that should be Okay, for the moment we leave that open. That comes in the next part, we deal with that. Here we need to do some cosmetics, make sure everything is aligned properly so that we can deal with it. And we don't need that anymore. Okay, here is the first problem we need to fix. That last move now becomes next move. And because we also add a different timing, we need to put it in each section here for up and down. So let's get started here. This now becomes millis plus our move delay, which by the way can go here. We don't need that because we now compare it to just like next move. So this becomes next move, and then this becomes millis plus move delay CL in that particular case, and then we can copy that line down here, and that becomes move delay TH. Okay, that should be good. Now there is one last problem we need to deal with, and that is right here. When we call this process servo function with this parameter here, what the processor does is it makes a copy of that entire line in the array and sends a copy to that procedure, which is bad because when we now make changes to the data, it does not make it back into the original array. Now there are two solutions to deal with that. First, we could, instead of sending the entire array, we just could send the index and then look up in the original array and do the processing and all that. The other possibility, I think, is more elegant. Instead of sending a copy, we send a pointer to that data. So the way we do that is we give as a variable, and we need to define that here anyway. That would be my servo, and we call it this servo. So this would be the static definition, and now we make it the dynamic definition. So a pointer operation by simply putting an asterisk in here. That means now it's not expecting a full set of data, but just a pointer to a memory location where it finds exactly that data. And we copy that, the same thing, into the definition of our process relay function. And down here we need to now send a pointer, and we do basically just a reference by putting in an ampersand. And now it's not sending a copy of the data, but just a pointer to that data. Unfortunately, up here now the syntax changes a little bit. So this now becomes this servo, and it's no longer a dot because it's now a pointer operation. It uses this arrow here. So let's replace that everywhere. Wherever it says servo array I dot, we replace that by this servo arrow. And here now we have a little problem as well, because we do no longer have that I anywhere, because the I is now in the process locations function. So, but we have now a port address in our this servo structure. So that's now port A. That was another reason why I wanted to have that port in here, that we can reference it very easy. Okay. And that's the last section now. This would be port A as well. And the last line. Okay, let's quickly glance over it, see if we have any obvious errors. That looks good, and that would actually be the last change I want to make. So let's try to compile it, see what happens. Okay, there is an error here. Oh yes, look, one of those dots not deleted. Okay, let's try again. Another one here. Oh, sure, it needs to be case. Stupid me. Okay. Okay, it compiles. Let's open the monitor while it's uploading. Okay, it's done with uploading. Okay, so let's test the first relay here, which is port or DCC address 24 from my handheld. It's moving up slowly here, and if I give it a thrown, it goes down fast. So that's what we expected. Now let's test for address 50, which is my second servo. It goes up fast and it goes down slowly. Again, what we expected. Let's quickly check the next one. Let's see what address it is. That would be 51 is missing. That would be address 10 on port 4. So let's select address 10. Close is fast. Thrown is fast. So that appears to work. Success. Let's go on with the implementation of the relay. So in the next step we are going to implement relay control. Before we do that, let's think about what are the differences between a servo and a relay. Well, first, a relay has only two positions, so it cannot really be used to display something that has like 31 aspects like on the signal. So what I'm planning on doing is blocking out relay commands from the signal aspects. I'm only going to allow relay commands to regular switch commands, which have just like two positions, thrown and closed, and that's it. So that means we need to block that from the signal commands. Make sure the signal commands only accept commands if it is for a servo, but not for a relay. The second thing is we just use thrown and closed, but nothing in between when it comes to a relay. So on the servo definitions we had those min pos and max pos. We are no longer going to use that. It's just 0 and 1. And the other very important difference is switch commands actually can be re-triggered. If you have like a slow motion switch machine that uses 4 or 5 seconds to go from one position to the other, and it's actually on the process of going there, and you send another switch command in the same direction, it can re-trigger that and make the activation time longer. And we need to somehow deal with that. So those, I think, are the most important things. Let's go back to our IDE and get that implemented. So the first thing we need to do is really moving over the support for our relay board from the example file. And what we need to do is, we already have the wire part, so we need to get that include, and we add it right up here. Then we need to have this definition here, and that goes right here, for example. Then we need to have the setup, so we can just copy over all that. That's identical. We have 16 ports that need to be initialized, so that goes into our setup process, which is at the end, I believe. Yes, here. So It can go right here, and we can actually copy that text to the end so that we know init port expander is done. That would be that. So I think that's it. Let's look over it. That the rest we will copy and use as we go. Okay. So the next thing we need to do is defining our positions. Let's go up here. We used to have servo min and servo max, and now we do two more defines. One would be thrown, and that would be 1, and the other one would be closed, and that would be 0. Could be the other way around, does not really matter, but we are going to use those. Okay, we already did the definition of the data type. Now we are going to add 8 more ports. Since we have 16 relays, we are going to add 8 relay drives, 8 relay addresses, so we make this 24. And that means we have to add 2 more groups to our definition. So let's first just do a prototype and then do some copy and paste. So the first one, and let's just select addresses, let's say starting with what is 361. Now that would be a relay, and the first port we are using would be 0, the next one is 1. We can now say this is now really closed. This is thrown, and our default position would be thrown, and the start current position would be closed to make sure that it's actually doing something. And we would say, well, let's deal with the timing later. So we need to copy that for the first group, and then we do an additional group, and we just give them like consecutive addresses from 61 to 68, and then we need to deal with the port numbers. Okay, and let's say now the first one would be a tortoise. Let's do this. When we put both times to 0, that means it stays on indefinitely. It does not switch off, so one of the relays is always on, and the drive is under power. So for a tortoise switch machine, that would be the way to go, because that's a stall motor. It runs into the mechanical stop and stays under power. Let's say we also have a motor that needs to be switched off, and we give it, let's say, 4 seconds in one direction and 2 seconds in the other direction, and then let's say the next one would be a 3-wire solenoid type that requires like 400 milliseconds for activation, and then the next one would be we can just copy that and say that's just like a quicker drive. So let's just go with the first 4. We have something for testing, and everything else we leave at 0. That means they stay on forever, which means one of the relays is always on. Okay, so that would be the definition. We already defined, now we have 24 drives in total. Now the next problem we have on the signal address here, we need to say if the address is, if there is an address match, and so we need to filter out all cases where we are not dealing with a servo. So we say servo array I dot drive type equals servo. If this is the case, and only then we are processing the signal command. Otherwise, we just go by, let it go. Okay, so that would be this. And then up here, that remains the same. There is one problem, well, we come back to that later. So then the process servo is, I believe, the same. There is no change. Now let's deal with the process relay command. So we know this process gets called when target position is not the same as current position. So it means a command comes in, sets the target position to thrown, the current position is closed, then and the DCC address obviously, or for that port number is the one we want to deal with. So it calls this process relay. And then when it comes in, it needs to distinguish whether it's like retriggering or just like a new setting. And this is something that is a little bit tricky. Let's look back to the process servo function there. We have that current position that basically moves towards the target, right? We set the target position, and then let's say the current position is 50 ticks off. So every time we go through it, it's moving it like one tick. So that means we have a current position that is different from the target position, and also different from the origin where we started off. So, but we can always check whether the current position is the same as the target position, and there is no retriggering there. When we deal with relays, it's a little bit different. We have two defined positions, and that's all. Everything else in between, we don't have an indication where it is. So we have to insert like an artificial current position. And that means when we receive a command, we always set the target position, and to make it move to activate the relays, we set the current position to the opposite. So let's actually change that up here. So if we are dealing with the current address, and it is actually a relay drive type. So we say drive type, drive type equals relay, and only then, not if it's a servo, but if it is a relay, we need to set our current position to the opposite of the target position. So that's actually not working because it's numbers. So we say if servo array current position equals thrown, then pos becomes closed. And if it's the other way around, our curl pos becomes thrown. Okay, so let's let me explain it again. We have the direction flag here, and we set our target position. Now the target position is set to the minimum pos if it is a servo, but it needs to be set to closed when it is a relay, so we need to change that here as well. We need to make that a function, the same function here. So we make this servo. If that drive type is a servo, target position becomes the min pos. Otherwise, it becomes the lower here, which would be closed. Okay, and then the same thing here. It becomes the max pos or thrown. Okay, so we set the target position, and then on top of that, if it is a relay, then we set the current position, and that needs to be target position here. So if the target position is thrown, then the current position is closed, and if it's the other way around, then the current position is thrown. And we actually could also combine that. That would be a little bit more condensed code. So we say our current position is, and we make this our decision function, and that would be, if it's thrown, then it becomes closed, and otherwise it becomes thrown. Okay, that's the same, technically the same, it's just a little bit more elegant. Okay, so let's see again. If the drive type is relay, and only then our current position, we set the current position to the opposite of the target position. So if the target position is thrown, we set it to closed, and if it's not thrown, then we set it to thrown, and it's the target position. No, it's the current position that we are setting based on the target position. So that allows now for re-triggering, because if it is just somewhere in between, we don't know what it is, because maybe the relays are still activated. We are basically going to tell the system, hey, you are in the wrong position, and that causes then the system to activate the coils in the right direction and start the process from the beginning. Okay, good. Now let's look into the process relay function. The process relay function now is a function of the value of the current position and the target position. If the current position is 0 or 1, that means a new command has been issued, as we just have seen before. So that means we need to activate the coils. And then when we activate the coils, we set the next timer, the next action timer, next move timer. And we also set the current position to a value that is not 0 and not 1. And when we come into that function the next time, we see it's actually in progress, so we just monitor the time. That's how we do it. So let's do that. We basically do a switch command. and we look for our current position. So that would be this servo arrow purpose, I believe it is, and we do a case 0, and I leave that open for the moment, and we do a case 1, which means the current position is 1, which already automatically means the target position is 0, because we only come into this procedure, as we see down here, if the target position is not the same as the current position. So if the current position is either 0 or 1, the target position is the other way around, and we need to take action. So we activate the coils, and we have seen that actually in our example how we do that. Let's go quickly back there. That would be a digital write, so we can copy this here. Let's go back. So we need to activate our port A. And we need to give it a high or a low depending on the target position. So we say target position can be 0 or 1. We can make that logical function as we can give true or false. So we say this servo arrow target pose equals thrown. That would be either a 0 or a 1 depending on what it is, and then we need to set port B, and let's actually take that back a little bit here. Port B, which is the other relay, needs to go the opposite way. We can say if target position is closed, then we set it true, otherwise we set it false. So this actually puts one relay on, the other off, or vice versa, and that's exactly what we need to bring that drive in either direction. And now you see why I actually leave that open. That's a little trick here. If I do this like that, case 0 and no break, it actually just continues with the next line. So if the current position is 0 or 1, it's basically going in here. And then the next thing that we need to do is we need to set our current position to a value that is not 1 and not 0. So we say it's x hex FFFF, which is all bits set to 1. So that's a value we can later recognize. And then we need to set the timer. Let's copy that. It needs to be millis plus, and here again we go with a distinction. If this servo purpose equals thrown, oh, it's actually not pose, it's target pose, then we would put in this, and the other way around it would get a CL, and that whole thing needs to be in parentheses so that it gets executed first. So it determines based on target pose whether what delay it actually should take, and it adds that to the millis function, and that calculates our time of the next move. And then we need to give it a break so that it actually stops execution here. It goes back to the loop, and then when it comes back next time, it's the current position here is neither 0 or 1, but it's hex FFFF. So we do a default which means in all the other cases that's what you do. And if it goes in here, we need to check if the time is up. So we can actually copy that from here. If millis is actually more than next move, that's the first criteria. And the other one is we only want to process that if the timer variables are not 0. So we say, we can actually take both of these for the moment. So we say this move delay TH is something else than 0. And we can make it both or just one. I opt for just one. So if at least one is not 0, we process it properly. Not equals 0. Oops. Okay, that goes around here, and then we give the priority to this OR function here. Okay, and then we need to have an additional parenthesis here. So if the next move is up and one of the delay times is something else than 0, means a delay time is specified somewhere, then we go in here. And what we do is we send a digital write. It's now time to switch that thing off. So we need all that. Let's see, this is port A. That becomes now a 1 to switch it off. Port B becomes a 1 to switch it off. And then the current position becomes now target position since the movement is completed. So we take this over. Okay, and then this whole thing here needs to be, of course, in one block. That is only executed if that statement returns true. Okay, let's compile it. See what happens. Okay, we have some warnings here. Oh yes, look, up here we are setting times of like 4000, 2000 milliseconds, and our delay times are actually only 8-bit variables, so we need to make these 16-bit variables. And now compile, upload, and see if it works. Okay, it's done compiling, it's uploading now. Okay, so now we should be able to control these relays. First 61, which really should stay on permanently. Yes, that looks good. Then 62. Now 62 should be 4 seconds in one direction and 2 seconds in the other direction. Okay, now let's try to re-trigger it, the 2-second activation. So I send more DCC commands here and it stays on, and as soon as I stop sending commands, 2 seconds later it switches off. That's good. The next one, 63, would be the 400 millisecond activation. So that's 400 milliseconds here. And 64 would be the 200 milliseconds. and that's 200 milliseconds. 65, and the next ones should be permanently on, and they stay permanently on. So everything working as expected. So the last thing I wanted to do is a performance analysis. I wanted really to know how many times per second this loop is actually running through, which gives an indication how responsive the decoder is going to be. So for this I do a define measure mode so that I can easily switch that on and off, and I do an if diff measure mode, and if that is defined, I do an integer loop counter, and I do 32-bit value loop timer. Okay, I make a copy of that, and we go down to the loop function. Here we go. So here we basically just go around and round and round, and I add a section where I actually would measure the number of loops and then print it out once in a second. So I do if loop timer is smaller than millis, so I do that every second, and I use the same thing for the loop timer. I add 1000 milliseconds next time when I'm running through. I do a 0 print line of my loop counter. Then I do a reset of the loop counter to 0, and I do a loop timer equals millis plus 1000, so that it gets executed every second. And in all the other cases I basically just increment the loop counter, so whenever I come through here I check the time. If millis is more than my current loop timer, I print out what it is, I reset the loop counter, reset the loop timer for another 1000 milliseconds, and then increment the counter, and that's it. And the whole thing only gets compiled in if that measure mode is actually defined, so it's very easy to switch that on and off. So now make your guess, how many loops are we getting? What would you think? How many times a second are we actually processing through the whole thing? Are we calling the DCC process, and are we processing all 24 array lines in our array? Last chance to make a guess as we are getting ready, and soon we will have some results. Okay, compiling is done. Uploading, rien ne va plus. Okay, it's initializing. 15,000, 16,000, close to 17,000. Now let's send some commands here, see if that makes a change. Not really, a little bit. So roughly about 16,500 times per second it is checking all the ports if something needs to be done, something needs to be adjusted. So that is actually quite fast, I would think. I'm always impressed how fast these little microcontrollers actually can go around, how much performance you get for just like $3. I mean, it's almost unbelievable. So with 2 more rounds of improvements, we now have a decoder that can deal with pretty much every switch machine that is available, be it servo-driven, magnetic or slow-motion motors. And best of all, addresses can be freely mixed according to your needs. So if on your layout you replace a coil switch drive by a servo type, you don't have to replace the decoder or change the address scheme of your layout, but you can simply make some adjustments in the software and that's it. And in my opinion, that is the way it always should be. The software of our devices should be flexible and configurable so that it can be easily adjusted to a wide variety of hardware configurations, and the efforts on the user side should be minimal. Okay, on that last part, this decoder fails as it requires the user to recompile the code, but that is due to the nano processor. If we would replace it by an ESP32, all these configurations could be done via web page. Same principle I demonstrated in videos number 11 and 14 for the CDC panel and the signaling system. Another improvement possibility would be adding local input buttons. In that case, it would also make sense to add a LocoNet interface for position feedback in case the user activates a turnout using a local button. Leave me a comment below if you have other ideas for useful features. As you have seen, there is plenty of computing power left to implement additional functions. As always, I hope this video was useful or at least interesting for you. If so, please click the like button below and subscribe to the channel. I appreciate your support as well as any feedback in the comments section below. Also, check out the additional information provided in the description section. If you don't want to miss any future IoTT videos, click the bell icon and you will get a notification when the next video comes out. Thanks for watching and see you next time.